All right, so this is the beginning of chapter 4, and in this chapter we are going to work towards solving what are called optimization problems, which are essentially problems where you're trying to find a maximum or minimum value usually in some kind of real-world scenario. So I'm going to start this lesson with an example. By the way, you can kind of ignore the extreme value theorem over here. We're going to get to that in a few minutes. So we're going to start over here. And we're going to start with an example, which I admit is kind of contrived. It's not a terribly exciting example. It's a little bit of a weird one, but it's going to be a perfectly fine problem to work with to kind of demonstrate a lot of the mechanics of what I'm teaching you about finding extreme values. So first of all, this first section is about finding extreme values. Now, extrema is just the plural of an extreme. I'll also use the word extremes. Extrema, I think, is a Latin plural. But extreme values mean maximums and minimums, right? So we talked, you probably remember from pre-calculus and also earlier in this class, we've talked about like local minimums and maximums versus absolute minimums and maximums, that type of thing. So let's dive into the example. In this example, we have a piece of wire. Okay, and I'm going to draw a straight line here to represent that piece of wire. Let's say that wire is 10 inches long. 10 inches. What we're going to do is we're going to take this wire and we're going to cut it somewhere. Okay, somewhere along its length we're going to make a cut. So let's say we make our cut right there. Cut. Then, depending on where we make that cut, we'll have some length. Let's call it x on this side. So x could be 0, which would be like we don't make a cut at all. X could be 1 inch or 2 inches or whatever, 2.5 inches, anything all the way up to 10 inches, which would be we kind of don't make a cut at all, except we're going to take the entire thing on the left versus the right. Okay, so what I mean by that is we've got x on one side, we've got the length on the other side that's left over is going to be 10 minus x, right? And then what we're going to do with these things, we're going to take each piece of wire and bend it. And we're going to bend the piece on the left, the one of length x, we're going to bend that into a square. So that's a square. And we're going to take the piece on the right, which is 10 minus x units long, and we're going to bend that into a circle. Okay. So now what we're going to do is calculate the area enclosed by the square and the area enclosed by the circle, and then look at the total area. And that is going to be the function we're going to be working with for this example. So to calculate area for square, we need to know the length of a side. So this is a square, so both sides, all sides are of length s. So what is that s going to be equal to? Well, we know that for this square, since we took a wire of length x and bent it into a square, the perimeter of the square has to equal x, right? So the idea is we cut the wire into two pieces and the first piece is bent into a square, right? So the perimeter is going to be the length of that piece of wire, which is x. So the way you calculate a perimeter in terms of a side length is it's 4 sides, right? So 4s. So 4s has to equal x, which means the side length of the square has to be x over 4. That's easy enough. Now the area of a square is equal to the length of a side squared, right? That's why we call raising something to the power 2, that's why we call it squared. So that would be the area of the square. I'm going to represent that with a subscript square, would be x over 4 quantity squared, like that. So there's one of the two areas we want to calculate. So now let's turn our attention to the circle. The way you calculate a circle area is with the radius, right? So we're going to need to know the radius of that circle. First of all, we know that the perimeter, since this circle was made by bending this piece of wire of length 10 minus x, the perimeter of this one is 10 minus x. And the perimeter of a circle is always calculated in terms of a radius by doing 2 times pi times the radius. Another word for perimeter for a circle is circumference. So you may remember the formula circumference is 2 pi r, or in other words, pi times the diameter. So 2 pi r is going to be 10 minus x. So now that means r, the radius, will be 10 minus x over 2 pi. Okay, now the area of a circle is always calculated by taking pi times the radius squared. Area is pi r squared. So the area of a circle, which I'll represent with a subscript circle, the area of this circle is pi times the radius, which was 10 minus x over 2 pi, and then squared. So now what we have is the area of the square and the area of the circle both as functions of x, so that wherever we cut this wire, determined by the value of x, we will now be able to calculate from that knowledge alone. Directly, we can calculate the areas of the two shapes. And so now our total area, adding these together, will be area of the square plus area of the circle, which is going to give us a function of x. A is a function of x equals area of the square, x over 4 squared, plus the area of the circle, pi times 10 minus x over 2 pi squared. Now, this function belongs in this section, which is extrema on a closed interval, because the domain for this function, think about it, the range of values that you can have for x would be anything from 0 to 10, right? 0 being on this side and 10 being on this side, right? So either if it's 0, then it's like the entire wire is going to be used to bend into a circle. Whereas if it's 10, the entire wire is going to be bent into a square, right? And if you cut anywhere in between, then you're going to have a square and a circle. So, that's a finite closed interval domain, which is 0 less than or equal to x less than or equal to 10, or in other words, 0 to 10, written in interval notation like that. That's our domain, which is why I'm going over this problem in this section. So now the question is, what's the max and min? What's the maximum and minimum area that these two shapes could contain? Okay, that's our question. So now we're gonna go over some theorems that are gonna help us answer that question, and then we're gonna come back to this example a few times as we go. So now let's turn our attention to this thing called the extreme value theorem. So first of all, one very theoretical question you could ask yourself is like, well, if I have a function on a closed interval, how do I know that it's even going to have a maximum or a minimum value? You know, you could have, maybe it's going to have a vertical asymptote and it's going to diverge to infinity, and then it doesn't have a max, right? So absolute maximums and absolute minimums sometimes don't exist. So how do I know I even have an answer to look for? Well, the extreme value theorem is a theorem which very simply just assures us that a minimum and a maximum will exist for a function on a closed interval as long as the function is continuous. Because the type of problem that could come up which would make it so that there is not like a minimum value would be one example would be a vertical asymptote, but that can't happen if the function is continuous. And the only other thing that might mean there's no like absolute max or min would be if the function just diverges off to infinity as x approaches infinity. Like for example in like x squared, right? It goes off towards infinity. But that's not going to be possible if we're only looking at it on a closed interval. Okay? So if we're only considering the function on a closed interval, on that closed interval, then it will attain a maximum and a minimum value. Okay? So this just assures us that the answer we're looking for does exist. So now, let's look at a picture. Let's look at just a generic picture of one possible continuous function on a closed interval. Our closed interval is going to be from A to B. Let's say at A we have a point up here, and at B we have a point down here, and in between it's going to do something like this. Okay, so there's a function. Now, looking at this function, we can see where the minimum and the maximum is going to be. The maximum is going to be right here. And the minimum is going to be right here. So what we can observe in this situation is that extreme values occur at only specific types of points. So extremes occur either at endpoints, like in this case the maximum occurs here at the endpoint when x equals a, all right? Or local extremes. Okay, and we're talking about absolute extremes here. I forgot to mention that. So absolute extremes occur either at endpoints or at local extremes, right? Like with these endpoints, you got a local extreme here. Here's another local max and a local min. Okay, those two don't happen to be absolute max or min, but they are local extremes. So like those are the candidates, all right? So if we're looking for the absolute max and min of the function on this closed interval, we should look for the endpoints and the local extremes. So endpoints are easy to find, all right? Endpoints, check. We got those. Those are always easy. There's just A and B values. Those should be given to you. Or, those should be apparent in the situation you're looking at. But what about the local extremes? Well, how do you find those? So there's two cases that we're going to look at. Well, there's really only two cases that can show up, because remember that the function we're dealing with has to be continuous in this situation. All right, we're not going to be doing this with non-continuous functions. So case one is when the function is smooth. If the function is smooth at a local extreme, I'm going to draw maximums for these pictures I'm about to draw, but they could be minimums, and it works pretty much the same way. So if you have a maximum and it's nice and smooth right there, then what's going to happen is you're going to have a horizontal tangent. Okay, so if that's our x value c, then in this situation f prime of c is going to equal 0. So that's one case, right? If it's smooth, the derivative at that max value, the derivative at that maximum point there is going to be 0. Case 2 is when it's not smooth. If it's not smooth, well then maybe it's still got to be continuous, right? So I can't make like a jump or a vertical asymptote, but what could happen is you could have like a corner or a cusp of some kind, like this here. So then, if that's our value c, it's c right there, then in this situation, f prime of c is undefined. Okay. So to find our local extremes, turns out what we're going to need to search for are all of the x values where f prime of c is either 0 or it's undefined. Okay, I'm going to continue this in the next video.